All right, in section 8.3, we'll be looking for applications of the differential equations to exponential growth. All right, so we're going to use differential equations to study real-life problems that have exponential growth. All right, so in many real-life situations, the growth of a quantity is proportional to the quantity f of t itself. So for example, if you invest money in a bank account, the amount that you get back from the bank will double if you double your initial value. So if you multiply the initial value, the initial investment by 5, then the amount of interest you'll get will be multiplied by 5 again. This is what this means. Hence, its derivative, f prime of t, is proportional to f of t itself. Hence, f of t is a solution to the differential equation. So f prime of t is a multiple of f of t. R here is called a constant that's called the growth rate. Right, so two famous examples of that follow this differential equation are, first of all, f of t is the value of an investment with a continuously compounded interest rate of r. Right? You could also have that f of t is the number of individual in a population with, this is only going to be true if you have unlimited resources. Okay, so nothing is impeding your growth. All right, proposition 8.3.1, the general solution of the differential equation f prime equals r f t is f of t is p is a constant, ERT. So I like to think of it as PERT. All right, so let's prove that. This is a separable differential equation. We'll replace it by dy over dt. My variable is t is equal to ry. When I separate the variables, I'm going to send the y on this side. I'm going to send dt on the right side. The r could go either way. It's a constant. It doesn't matter. It's simpler just to leave it where it is. All right, then we integrate both sides. Integral of 1 over y is log of absolute value of y. The integral of a constant is that constant times t, and I need a plus c somewhere. All right, I don't have initial condition, so nothing to do for 4. So let's move to 5. I need to isolate y. So if I apply the exponential to both sides, that's going to give me absolute value of y. And then to get rid of the absolute value, I could take plus or minus. All right, so this is not bad, but it doesn't quite look like what I want. I have e to the rt, the plus c I don't really want. So what I'll do is I'll write this as e to the rt times e to the c. And then what I'm going to have is some constant here, plus or minus e to the c. That's just a number, and I'm going to call it p. So I get y is p rt, and so the answer, it is in fact PERT. All right, so that's proof. This means as soon as we're talking about continuously compounded interest, or we're talking about the growth of a population with unlimited resources, or it's called, then we'll be using this model right here. All right, so we say that a function has exponential growth if f of t is PERT. And then r is called the rate of growth. It's also called the interest rate in the specific case of continuously compounded interest. All right, let's look at an example. All right, example 8.3.1, Brigitte invests into an account where interest is compounded continuously. Assume that her investment triples in 20 years. Assume also that after 5 years she has $10,000. All right, so I'm going to let's take f of t to be this amount of money after t years. We're asked to figure out what that is. Find the amount of money after t years. And so we know that it has to follow PERT. I need to figure out what P is, and I need to figure out what R is. What's the growth rate? I'm not given that. What I am given is that F of 20, investment triples in 20 years, so that's 3 times F of 0. And I'm given that F of 5 is 10,000. All right, so this is what I have. I need to figure out what P is and what R is. So let's start with the first one. So F of 20, that's PER20. F of 0, that's PER0, that's just P. And so what I know is that PER20 should be 3 times P. And now I can solve for R. The two P's will cancel. I can apply log on both sides. So log of e to the R20, that's log of 3. And so this will cancel with the e. 20R is log of 3. And so that gives us that R is log of 3 over 20. All right, good. Let me shrink this a tiny bit. I'll give you more room. And then I'm going to use the final piece of data. After 5 years, she has $10,000. And so 5 years, that's f of 5, which is P E R I have. R is now log of 3 over 20. That's what we solved for right here, times T times 5. And I know that that's $10,000. And so P is $10,000 divided by E. I can cancel part of the 5 with part of the 20, and I'll get log, oh, sorry. Let's get back to black. So log of 3 divided by 4. All right, so we get that f of t is 10,000 over e log of 3 divided by 4, e log of 3 divided by 20 times t. All right, so I like to keep the constant as precise as possible. If you want, you can round it, but make sure to use enough decimals to have the right answer. When I ask you for specific numbers, like real life values and all of this, I'm going to ask you to round it with 2 decimals, and so those 2 decimals have to be right. All right, so the safest way is just to keep everything as is. You can also simplify here. Notice that I have e to the ln of 3 to the 1/4, so I could write this as e ln of 3 1/4, and that's 3 to the 1/4. Same thing here, that will be 3 t over 20. All right, so you could write it like that if you want to. Here are the questions that are left. What was Brigitte's initial investment? What interest rate is she getting on this investment? So initial, that means times 0, and so that's going to be 1,000, 10,000 e ln of 3 over 4 times e to the 0, and so that's just p. In fact, that's always going to be P. P is the initial investment. And so in this case, when I plugged into a calculator, I get 7,598 and I have 36 cents. Right? Again, if you want WebWork to accept your answer, you'll have to round correctly. So when it's money, 2 decimals. So that's the initial investment. And then the rate, interest rate, that's just R. And so we said that was ln of 3 divided by 20. I got 0.0549. And so that's, well, actually, that's about 5.49%. All right, so how long would it take until Brigitte has $20,000? So we're really asking when f of t, which is this mess, when this is 20,000. All right, so I'm going to send everything that doesn't depend on t on the other side. That's 20,000 divided by 10,000. That's going to simplify nicely. So I'll be left with 2e ln of 3 divided by 4. I want to go after the t, so I'm going to apply log to both sides. I'll get ln of 3, 20t is log of 2e ln of 3 divided by 4. Of course, this would simplify nicely, but you don't actually need to do it, right? You could leave it like this, plug this in your calculator, and you should be getting 17.6186 years. So again, this is an approximation. Whenever you have a real life question, then you should use an approximation to make sure that it makes sense. Does it make sense that it takes 17 years? Well, she started with 7,000. We know after 5 she had 10. Yep, it should take longer. 17 sounds good. And so you can even, if you want to, you could leave it in terms of years, but I like to put it in terms of months as well. So I calculated that 0.6 multiplied by 12 gives about 7, so 7 months. That's how long it would take.